Hello everyone, this is the second part of lecture 9. In this lecture, we're going to learn how to find the equation of a plane in three-dimensional space. Intuitively, a plane is a flat surface with infinite extent in all directions. If you have three non-collinear points, they are not on the same line, that could determine a unique plane in three dimensions. A plane in three-dimensional space is also uniquely determined by one point in the plane and any non-zero vector that orthogonal or perpendicular to the plane, and that orthogonal vector is called the normal vector. So that kind of a quick review of what we're going to study in this lecture. So hopefully after this lecture, we would be able to write the vector and scalar equation of a plane through a given point with a given normal vector. And we're going to learn how to determine if two planes are parallel or orthogonal. And we will learn how to determine or find an equation of the line formed by two intersecting planes. So now we're gonna go into the description of a plan. Before we go into the plan, I want to briefly talk about a line. So a line is determined by two distinct points. This is true for both cases of two dimensions and three dimensions. And a line can also be determined by a point and a direction vector along the line. So this is what we learned in the last lecture, where we use a point and the directions vector to form a parametric equations of a line, to symmetric equations of a line, and the vector equations of a line. And a plane is determined by three non-collinear points. That means these 3 points are not on the same line. Or it can be determined using two distinct intersecting lines, or it can be determined using a point and the orientations or a normal vector. So what is a normal vector? So a normal vector n of a plane is the vector that is orthogonal to every vector that lies in that plane. Let's take a look at this image. You have the three-dimensional space, and you have a plane here in brown. A normal vector n is equal to a, b, and c. This normal vector is actually perpendicular to the vector p0, p. And as a matter of fact, this normal vector is going to be orthogonal to every vector that lies inside this plane. So that's the definitions of the normal vector. When you have a normal vector, it will give you the directions on which the plane is facing. The next definitions I want to talk about is a plane in three-dimensional space. So given a fixed point p0 and a non-zero normal vector n, the set of points p in R3 for which the vector p0p is orthogonal to n is called a plane. So that's the definitions of a plane in R3, and we're going to use this information of the normal vector that is orthogonal to the vector p0p to derive the equation of the plane. So suppose p0 equal to x0, y0, and z0, and p is equal to x, y, and z are 2 points on the plane. Then you can calculate the vector p0p as follows. This is equal to x minus x0, y minus y0, z minus z0. And by the definitions of a plane in R3, the normal vector n is going to be orthogonal to the vector p0p on the plane. So the normal vector n of the plane is orthogonal to the vector to p0p. And when that is the case, we're going to apply the dot product between these two vectors. If you go back to the lecture of the dot product, you will see that if the two vectors are orthogonal to one another, or they form a 90-degree angle, then the dot product is equal to 0. So you have n dot with p0p going to be equal to 0. So this is the scalar value. Given that n is equal to a, b, and c, and p0p is equal to this vector. So when you look at this notations right here with the pointed bracket, this is another notation for you to write the vector. You can use this notation, or you just basically use parentheses that we have been using so far. It's just that you have to be aware with the context that it get applied, right? For the context of a point, right? So this value is going to represent the component of a point. In the context of a vector, this component can represent the component of a vector. All right, so n is equal to a, b, and c, and p0p is equal to this component. And we're going to perform the dot product between these two vectors. That is a, b, c dot with x minus x0, comma y minus y0, comma z minus z0, and is equal to 0. So when you perform the dot product, you're going to get that a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0. So this equations that we just obtained right here is called the standard or the scalar equations of a plane. Now, in addition to that, what you do is you can distribute a into the parenthesis, b into the parenthesis, and c into the parenthesis. We got ax minus ax0 plus by minus by0 plus cz minus cz0 equal to 0. And I'm going to group ax plus by plus cj together, and minus ax0 minus by plus by0 plus cz0 together, and with the negative as a common factor. And in fact, I'm going to move this value to the right hand side, and I got ax plus by plus cz equal to ax0 plus by0 plus cz0, and I'm going to let the right hand side equal to d. Why that is the case, remember the normal vector consists of a, b, and c, so a, b, and c are just constant. In addition to that, x0, y0, and z0 are some constant or the component of the point p0. So together, this value is a constant, so therefore it makes sense to substitute this value on the right hand side with d. So you get ax plus by plus cz equal to d. So the equation we just got is called the general form of the equation of a plane, or linear equations of a plane. So this is the general form of the equation of the plane. Or linear equations of a plane. Or we can call it the general linear equation of a plane. When you look at this picture, and you can see that the left hand side of the equations are the same. The difference is that they have different right hand side values. If that is the case, you can see that these three planes are called parallel lines. Okay, and we get to that a little bit later. Next, I'm going to give the different equations to form a plane. So given a fixed point P and a vector n, this is the normal vector, the set of all points Q satisfy the equations n dot with PQ equal to 0 forms a plane, right? So that is what we did here in the derivations. Because the normal vector and the vector on the plane are perpendicular to one another or orthogonal to one another, so therefore the dot product is equal to 0, and from there we can derive the equations of a plane. This equation is known as the vector equation of a plane. And then the scalar equation of a plane with the normal vector n equal to a, b, and c containing the point P, x0, y0, and z0 is given as a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0. Again, this is a scalar equation of the plane with a normal vector n containing the point x0, y0, and z0. And from the scalar equation, you can manipulate the equations and arrive at the equation of the form ax plus by plus cz equal to d. And this equation is called the general form of the equation of a plane, or a linear equations of a plane, or the general linear equations of a plane, where d is equal to ax0 plus by0 plus cz0. Okay. Now we're gonna use this information to tackle the first example. So in example 1, we want to write an equation of the plane passing through the point 4, -2, 1, and orthogonal to the vector n, 1, 2, 1, in both scalar and general forms. So we'll start with the scalar equations of the form. Ax minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0, given that a is equal to 1, b is equal to 2, and c is equal to 1 again. And x0, y0, and z0 are 4, -2, and 1. So you got 1 times x minus 4 plus 2 times y minus -2 plus 1 times z minus 1 is equal to 0. So if you manipulate these equations or simplify this equation, you get x minus 4 plus 2 times y plus 2 plus z minus 1 equal to 0. So this one is the scalar equations of the plane. Now we again can manipulate this equation further to arrive at the general form or general linear equations of the plane as follows. So you have x minus 4 plus 2y plus 4 plus z minus 1 equal to 0. So you got x plus 2y plus z. The -4 and 4 cancel out. You're left with -1 by itself. You're going to move that to the right hand side and you get this equation. So x plus 2y plus z equal to 1 is the general form of the equation of a plane. So this equation is the general form of a plane, or a linear equations of the plane. Okay, so hopefully that should be easy for us to follow. Now in the next example, you are given 3 different points, and these 3 different points are non-collinear. These 3 points are not on the same line. Now to find the equations of the plane containing 3 points P, Q, and R, what you do is that we first form the 2 vectors PQ and PR, and then you can calculate the normal vector of the plane from these 2 vectors using the cross product, because when you do the cross product will produce a vector where the vector is going to be orthogonal to both PQ and PR. And because a vector that is orthogonal to a vector in a plane, or any vector on the plane for that matter, then that vector is the normal vector. With the normal vector and the point on the plane, you can write the equation of the plane in scalar form or in the general form. So first, we form 2 vectors on the plane as follows. We form 2 vectors on the plane as follows. So you get PQ is equal to 0 minus 1, 2 minus 1, 1 minus -2, and you get this one to be -1, 1, 3. And you're going to form the vector PR, where the components are -1 minus 1, -1 minus 1, and 0 minus -2. So you got -2, -2, +2. So you get 2 vectors on the plane, And to find the normal vector, you're going to find the cross product between these two vectors. And the cross product will be orthogonal to both BQ and PR. So that is a normal vector of the plane is calculated as, so you have n equal to PQ crosses with PR. You use the determinant approach to calculate the cross product of these two vectors. So if you have two big vertical line here, this is a 3 by 3 determinant, so where the first row is I, J, and K, which are the standard unit vectors. The second row consists of the component of PQ, which is negative 1, 1, 3, and for the last row consists of the component of PR, which is negative 2, negative 2, 2. Then you start with the first entry, which is I. When you choose I, remember to delete the corresponding column and delete the corresponding row, and you get the 2 by 2 determinant of the form 1, 3, negative 2, 2. Then you move on to the second entry, which is J hat. When you change the row, you change the sign as well. And remember, you remove the corresponding column and the corresponding row of J. And you get negative J hat times the 2 by 2 determinant of the form negative 1, 3, negative 2, 2. And for the last term, you choose K. And when you change the column, you change the sign as well. So from negative J hat, you turn it to positive K hat. Remove the corresponding column of K, remove the corresponding row of K, and you left with the 2 by 2 determinant of the form negative 1, 1, negative 2, negative 2. So the entry of I, or the coefficients of I, is equal to 1 times 2 minus negative 2 times 3 minus J hat times negative 1 times 2 minus negative 2 times 3 plus K hat times negative 1 times negative 2 minus negative 2 times 1. So if we do the calculations correctly, we get that the coefficients of I is 8. So AI minus J hat times 4 plus K hat times 4 as well. And therefore the normal vector is going to be 8, negative 4, positive 4. And with the normal vector and a point on the plan, so I'm going to choose the point P. You can choose any point that you like, doesn't matter. So we're going to start with the standard equations or the scalar equations of the plane. So the standard equations of the plane given n equal to 8, negative 4, 4, and p equal to 1, 1, negative 2 is going to write the formula again. So a times x minus 0 plus b times y minus y0 plus c times z minus z0 equal to 0. For a, b, and c are equal to 8, negative 4, 4. x0, y0, and z0 is equal to 1, 1, negative 2. So the equation becomes 8 times x minus 1 minus 4 times y minus 1 plus 4 times z minus negative 2 equal to 0. And again, this is the standard equation. This is the scalar equation of the plane. You can stop right here if that is the only questions that they ask. But we can actually manipulate this equation further to arrive at the general form of the equation of the plane. Or you can continue with ax minus 8 minus 4y plus 4 plus 4z plus 8 equal to 0. And we're going to do ax minus 4y plus 4z equal to negative 4. And this is the general form of the equation of the plan. So this is the general form. Now we're going to move on to the next topic, which is about parallel and orthogonal planes. So two distinct planes may be parallel and two intersecting planes may be orthogonal. So in the first case, the two distinct planes are parallel if their respective normal vectors are parallel. If their respective normal vector are parallel. In the context of two vectors that are parallel, you can write n1 in terms of t times n2, for t is a parameter or a constant for that matter, or a scalar for that matter. So n1 can be written as a scalar of n2. And the two planes are orthogonal to one another if their respective normal vector are orthogonal. So when the two vectors are orthogonal, that means the dot product of the normal vector has to be 0. So that is the dot product of the two vectors, or of the normal vectors, is 0. So in this case, you have two planes, one in brown and one in green. You have two normal vectors, n1 and n2. These two planes are orthogonal to one another. Then you get that n1 dot with n2 is going to be equal to 0. Now in the next exercise, I want to find the equation of the plane that passes through the point -2, 4, 1. And is parallel to the plane 3x minus 2y plus z equal to 4. So to form a plane, you need a point and a normal vector. And the plane that we need to find is parallel to the plane 3x minus 2y plus z equal to 4. Suppose L1 is P1 is the plane that we are looking for. Is the plane 3x minus 2y plus z equal to 4. Then since P1 and P2 are parallel, then you have that n1 equal to n2. Here we assume that the scalar multiple of n1 and n2 is going to be equal to 1. Thus, n1 is equal to n2 equal to the vector 3, -2, 1. With a point and a normal vector, you can write the equation of the plane passing through the point -2, 4, and 1 with the normal vector of 3, -2, and 1. Then we have that a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0, given that a, b, and c is 3, -2, 1, and x0, y0, z0 is -2, 4, and 1. So you get 3 times x minus -2 minus 2 times y minus 4 plus 1 times z minus 1 equal to 0. Let's manipulate this equation. Let's simplify this equation a little bit. So you get 3 times x plus 2 minus 2 times y minus 4 plus z minus 1 equal to 0. So you can stop right here. This is the scalar equations or the standard form of the plan. Or you can manipulate the equation further to arrive at the general form of the equation of the plan, but there's no requirement on that. So we're going to move on to the next example. So in example 4, we're going to find an equation of the line of intersections of the plane Q and R. The plane Q has the form of x plus 2y plus z equal to 5, and the plane R has the form of 2x plus y minus z equal to 7. For the plane Q, I'm going to form the normal vector that is equal to 1, 2, 1. And the normal vector of the plane R is nr equal to 2, 1, negative 1. And if you notice these two normal vectors, you see that they are not multiples of one another. So therefore, you can conclude that the two planes are not parallel, and in fact, they intersect one another. And because of the intersections, they form a line. So since NQ and NR are not multiples of each other, we can conclude that Q and R are not parallel. In addition, they intersect one another. Then the intersection forms a line. And this line is what we are looking for. So there are different ways to find the equation of a line in this context, but I'm going to approach this particular procedure. So to find the intersection line, we do the following. To find the intersection line, we do the following. You're going to move from these two equations. You're going to move the constant to the left-hand side, and here the constant to the left-hand side, and you have a system of equations as follows. You get x plus 2y plus z minus 5 equal to 0, and 2x plus y minus z minus 7 equal to 0. And from these equations, we're going to solve for x in terms of z, and we're going to solve for y in terms of z. And we will let z be a free variable, where you let z be a parameter, when you can vary the value of the parameter. So from the first equation, you can solve for x and y in terms of z as negative z plus 5. From the second equation, you do the same thing. You get 2x plus y equal to z plus 7. And now you have a new system of two equations with two unknowns, because again, we want to set z as the free variable, so z is no longer a variable that we need to worry about. Now from here, we're going to solve for x in terms of y and z. Again, the goal is to solve for x in terms of z only and y in terms of z only. By solving x in terms of y and z at this step, eventually we can get to our answer of x equal to z only. So from the first equation, so from 1, we get that x is equal to negative 2y minus z plus 5. Then we substitute x into the second equation. We get that 2 times negative 2y minus z plus 5 plus y equal to z plus 7. And then you can manipulate the left-hand side and then combine like terms. You get negative 4y minus 2z plus 10 plus y equal to z plus 7. Now our job is to solve for y in terms of z. So you get negative 3y equal to 3z minus 3, and you can divide both sides for negative 3, and you get y equal to negative z plus 1. Now you have y in terms of z only. You can substitute y back into this equation, and you get then x equal to negative 2 times negative z plus 1 minus z plus 5 equal to 2z minus 2 minus z plus 5. You get z plus 3 for the answer. X is solved in terms of z only, and y is written in terms of z only. Here what you do is you let z be equal to t, which is a free variable in this case. Then we can write the parametric equations of the line as follow. So you have x equal to t plus 3, y is equal to negative t plus 1, and z is equal to t. As a matter of fact, if we follow the form that we used in the last lecture, we can write x as 3 plus 1t, y equal to 1 minus t, and z is equal to t. So this is the parametric equations of the line with the point 3, 1, 0, as you can see here in the image. And the directions vector 1, negative 1, and 1. That's how you find the equation of the line of intersection between two planes.